We know that the Higgs boson is a carrier for the Higgs field that creates mass. But what does it decay into? The most common is a bottom and an anti-bottom quark, but we can't measure it, so we'll move on to different ones. Decay into two Z bosons, but we can't really directly measure this, so we can measure what they decay into, which is two muons or two electrons. And lastly, the Higgs boson can decay into two photons, but this is rare. I'm most concerned about this and this. Why is that? And how do we know that it's 125 gigaelectron volts? Well, gigaelectron volts is a unit of energy. And we measure energy of particles through calorimetry. A technique for measuring calorimetry I've had a part in developing is called the Shashlik detector. So, how do we measure the energy of particles in general? Well, the most significant type of energy a particle could have is kinetic energy. So, in order to measure this type of energy, we must stop the particle. How does this detector do that? The Shashlik detector has three main parts: a tungsten plate, a lyso crystal, and a fused silica capillary tubes. The combination of tungsten, which is a very dense element, and a lyso crystal, which stands for lutetium yttrium sulfate doped with cerium, makes a special property when the dimensions are right. The dimensions of the tungsten are 14 by 14 in the square, and the thickness of 2.5 millimeters, which is the important part. Lyso is also 14 by 14, but it's 1.5 millimeters thick. When you combine the 2.5 millimeters of the tungsten and the 1.5 millimeters of the lyso crystal, there's 4 millimeters. Simple math. What does this mean though? This is the radiation length of the tungsten and the lyso crystal combined. The radiation length is important for two properties. With the electron, when this passes through the tungsten and the lyso crystal, it undergoes a special phenomenon called Bremsstrahlung. Bremsstrahlung is when an electron passes through this material of a certain thickness, and it will brem, or it will create another electron of a lower energy and a photon. Photons, however, undergo pair production with right radiation length. Pair production is when the photon passes through and then an electron and a positron pair come out. It is the electron and the positron pair because it is to conserve charge. Photons are neutral, and an electron and positron, plus and minus, will add up to zero, a net charge of zero. The electron here, there's still conservation of charge because the electron is still negative and the photon is neutral. Also, what is conserved is momentum. There are 30 layers of these, and after one layer there'll be two particles. After two layers, through Bremsstrahlung or pair production, there'll be two squared particles, or 4. After 3 layers, there are 8. This continues to about 2 to the 9th, where there's a peak of around 1,024 particles. What happens when this 2 to the 9th peak is reached? Well, as I said before, when this electron undergoes Bremsstrahlung, it loses energy creating this photon. And when this photon undergoes pair production, it has to split its energy in order to make an electron and a positron. So, at some point, like the 2 to the 9th peak, these particles may not be able to have enough energy to either undergo Bremsstrahlung or pair production. So, the dense tungsten will stop it, but not all at once. However, the farther down these particles go into the Shashlik, the more likely they will be stopped. This is a lot of particles, and with it, it creates an electromagnetic shower. Why do we need so many particles? Well, this is where the lyso crystal's special properties come in. It is a scintillator, which means if a particle passes through it, it lights up. Well, what's so special about lighting up? This is where the fused silica capillary tubes come in, like one right here. It has three main components to the liquid part of it. It is made of fused silica, which is a very high index of refraction, 1.57. The liquid part inside of it is made of three components: DSB1, mineral oil, and pseudocumene. DSB1 is a liquid wave shifter, which I will explain in just a bit. Mineral oil is the bulk of it. It's just a carrier, it's inert, it raises the flash point so it doesn't suddenly explode or catch on fire in the higher temperatures. Pseudocumene, it allows for the DSB1 to be dissolved inside the mineral oil. The DSB1 is a liquid wave shifter, like I just said. It can take a wavelength of light from the lysocrystal, and when this lysocrystal's light comes through the capillary tube and connects with the DSB1, it'll be around 430 nanometers, but it's never exact. So the DSB1 gets excited when it's hit by a photon of this wavelength. The molecule will sort of get excited and change. And when it does this, it releases a different photon of light at 490 nanometers. And this is the important part, because at 490 nanometers, now the light will traverse through the capillary tube to a photosensor. And this photosensor will read the light at the same wavelength from the capillary tube, but it will be a different intensity. And the intensity is the important part, because if we take a graph of the intensity versus the distance of the Shashlik and of the capillary tube, we can measure this through intensity, and we can measure this with the 2 to the 9th particle at the peak of the distribution. And when we take an integral of this curve, we can get the total energy of all the particles together from this electromagnetic shower. And the total energy of the particles is equal to the initial energy of this initial particle. And so, when this electron or photon first collides with this tungsten plate, it will create an electromagnetic shower through Bremsstrahlung or pair production. The lysocrystals will read the light and will scintillate. The scintillation and the light coming from it will hit the capillary tubes, and it will wave shift into 490 nanometers, which will traverse to photosensors, where we can read the intensity of the light and get the energy of the particle. So this is a real-time Shashlik. This is the 14 by 14 square, and this particular one is 29 radiation lengths long with an additional tungsten plate at the end, making it 118 millimeters long. This is the side where the electrons or the photons come through, and this is the side that faces the photosensors. There are typically 4 capillary tubes per Shashlik. Each capillary tube is a millimeter in diameter. So the liquid is inside of these, and they fit in a hole with the same length of the Shashlik that is 400 microns long. So there's not a lot of DSB1 inside of them, but they still have a lot of effect. Let's see that.